Welcome back. In the last few videos, we have been studying recurrence relations. So, recurrence relations is basically an equation that recursively defines a sequence of values. There are some initial terms, and the nth term is defined as a function of the preceding terms. Now, recurrence relations has been used extensively for combinatorics, analysis of algorithms in computational biology, in theoretical economics, and in various other subjects. In the last week, couple of videos earlier, we saw how to use recurrence relations for modeling some of the counting problems. Now, once you model some of the counting problems, you have to solve the recurrence relations in some way. So here are some of the examples that appears in real life. Say for example, t1 equals to 1 and tn equals to 2 plus tn minus 1. Or t1 equals to 2 and t2 equals to 3 and tn equals to tn minus 2 plus tn minus 1. Or this is the one that came from the Tower of Hanoi problem. T1 equals to 1, h1 equals to 1, h2 equals to 3, and hn equals to 2 times hn minus 1 plus 1. Or this is the one that comes from the Fibonacci sequence. f1 equals to 1, f2 equals to 1, and fn equals to fn minus 1 plus fn minus 2. So this one that comes from the binary search algorithm. b1 equals to 1 and bn equals to bn over 2 plus 1. Or this one that comes from the merge sort algorithm. m1 equals to 1 and mn equals to 2 times mn over 2 plus n. Or this one which comes from what is known as the Catalan number. C1 equals to 1 and Cn plus 1 equals to summation I equals to 0 to n Ci Cn minus I. Now these are some of the recurrence relations that appears in real life. These are the very small sample of them. Now the main question is, how do you solve this recurrence relation? So these recurrence relations are of course used to model various problems, but once we model them into recurrence relations, the next step is to solve them. In the last video, we saw a technique of solving them, and we told this was the technique that first of all guess the solution and then prove using induction. We saw that if we can guess the solution correct, then proving it by induction is possibly not too hard a problem. It is like the typical induction problem. The main issue is, how do you guess the solution? Now, guessing the solution can really be a challenging problem. So we will be dedicating quite a number of lectures on guessing the solution. Today we will be looking at the first and the simplest technique of guessing the solution. So here is it. So technique 1, the idea is just unfolding the definitions. What do I mean by unfolding the definitions? So let's look at some of the examples and you will understand what I mean by that. Note that these are not formal proofs. These are mere guessings which might work or might not work. And whether it works or not, of course we have to go back to the induction and prove it. And only then we get a formal proof. So this is whatever I am going to say now is how to guess this value. Say if t1 equals to 1 and tn equals to 2 plus tn minus 1. So let's write down here. So tn equals to 2 plus tn minus 1. Now what is Tn minus 1? I can recursively now open up, right? So Tn minus 1 is 2 plus Tn minus 2. Okay, let's write down once again. 3 plus Tn minus 3. Okay, let's write down once again. Plus 2 plus Tn minus 4. Now this is where comes up the big leap of faith. You kind of say that, okay, when there are some 4 of the 2's here, I have a 4 here. When I have 3 of the 2's here, I have 3 here. When I have 2 of the 2's here, I have 2 here. When I have 1 2 here, I have 1 here. So if I keep on doing this way, I will get up 2 plus things for some k of them plus Tn minus k. Now this is a leap of faith. Okay? Again, I told you, as I told, it's a guessing work, right? Now this number will somehow have to vanish. The idea is that the initial things T1 here, T1 equals to 1 gives us the hint. So we have to set. So here, if k equals to n minus 1, then Tn minus k equals to T1 is equals to 1. So I have to put this one as n minus 1. So in fact, if I remove this k here and instead I write here n minus 1 and I remove this one n minus 1, what do I get? Here I should get 2 times n minus 1 because I have 2 n minus 1 plus T1, which is 2n minus 2 plus 1, which is 2n minus 1. Okay. So this, by doing so, we have guessed that Tn equals to 2n minus 1. Again, although it might seem very formal way of proving that Tn equals to 2n minus 1, the fact is that it's still not a correct proof or complete proof because we have this dots here. Because there was a big leap of faith from this to this. Maybe our intuitions are correct and we get the right answer, and in which case we go ahead and prove it using induction. Right? And there are times, there are examples where this leap of faith may not be exactly correct. But this is one way of kind of guessing what the number is. So in this case, we have Tn equals to 2n minus 1 is the guess, and we prove it by induction. We have seen it in the last video that this is indeed the right way of guessing it, and we have our right guess by proving it by induction. Now let's move on to the next example. So here, Tn equals to n plus Tn minus 1. Again, we have to let us keep on unfolding the definition. So Tn equals to n plus Tn minus 1, which is equal to n into n plus. Now if I unfold this Tn minus 1, this is n plus 1 plus Tn minus 2. Now again, if I unfold it more, this is n minus 2 plus Tn minus 3. And here again, now let's do a leap of faith. As you see here, that if when I have 3 here, I keep on doing it till 2. When I have 2 here, I keep on doing it till 1. So maybe if I keep on doing this thing till n minus k, I have Tn minus k plus 1, right? Sorry, Tn minus k plus 1. Now again we have to somehow disappear this term. So the idea is again that we have to get this n minus k plus 1 as t as 1. So in other words, if I take k to be equals to n minus 2, right? What do we have? Then n minus k plus 1 equals to 1. So in that case, what should we get is that I keep on doing it plus n minus k, which is n minus 2, plus t of 1. Now t of 1 equals to 1, and this keeps on going, and this n minus 2 is nothing but 2, and the t1 equals to 1. So in fact we get the sum over the first n integers, which is n into n plus 1 by 2. So by doing so, we have guessed that t of n is equals to n into n plus 1 by 2. Now again, as I told you, this is a leap of faith because there was a leap of faith here, and hence this is just a guess. So formally proving it, we have to solve it by induction and verify that our guess is indeed right. Right? So again, the simple idea is keep on unfolding the definition and you will possibly be able to guess the value. And in this case, we did guess Tn equals to n into n plus 1 by 2, and we then prove it by induction. As I told you, most of the time the guess work does work correctly if we can unfold it in a right way. Let's look at one more example. This is the Tower of Hanoi problem, and where h1 equals to 1 and hn equals to 1 plus 2 times hn minus 1. Here hn equals to 1 plus 2 hn minus 1. Now this is actually quite interesting. So this one is 2 times, now here 1 plus 2 times hn minus 1, sorry, n minus 2, which is 1 plus 2 plus 2 times hn minus 2. Sorry, not 2 times. This is in fact 2 times 2, which is 4 times. Let's try to open it again. 1 plus 2 plus 4 times, what is hn minus 2? Is 1 plus 2 is hn minus 3, which is 1 plus 2 plus 4 plus 8 hn minus 3. Now this is where you really have to take a leap of faith. So let's write this one here. 1 plus 2 plus 4 plus, what is 8? 8 is 2 power 3 hn minus 3. Note that here it was also n minus 2 power n, 2 power 2, and I had 2 here. Here 2 power 1 and I had 1 here. So again, by the complete leap of faith, we can write it as 1 plus 2 plus 4 plus 8 plus 2 power k plus 2 power k plus 1, and when I have k plus 1, I have hn minus k plus 1. Now, here again we need to make this one disappear. So again I have to, and I have h1 equals to 1. So again I take k to be equals to n minus 2. If I take k to be equals to n minus 2, then n minus k plus 1 is equals to 1. So then this becomes t1, this becomes t1, which is 1. So I get 1 plus 2 plus 4 plus 8 plus 2 power k, which is n minus 2, plus 2 power n minus 1 times t1, and since t1 equals to 1, so I can forget this statement. And so I get this number, which is a GP series, and the GP series adds up to 2 power n minus 1. So I guess that Hn is equals to 2 power n minus 1. So this one clearly was slightly more complicated than the earlier ones. But again, here there was a massive leap of faith here when we guessed that I can this 3 3, and similarly here 2 2 and so on exist. And so by doing so, we have managed to guess it, but we need to prove that the guess is right again by induction. It so happens that in this case, the guess is indeed right, and we saw it last time that we can guess this one, and we do get the induction. By induction, we can prove this statement. So the basic idea that we learned from this video is that if you are given a particular recurrence relation like this, and if you can unfold it, maybe you can try to guess the number. The problem is that there are complicated ones like this, fn equals to fn minus 1 plus fn minus 2. Now we can try to unfold it by saying that okay, fn equals to fn minus 1 plus fn minus 2. Then fn minus 1 equals to fn minus 2 plus fn minus 3 plus fn minus 2. So I get 2 times fn minus 2 plus fn minus 3, which will give me 2 times fn minus 3 plus fn minus 4 plus fn minus 3, which is equals to 3 times fn minus 3 plus 2 times fn minus 4. And of course you can keep on doing it, but then as you can see, I can write down the next step directly, and this will become something like 5 fn minus 4 plus 3 fn minus 5. There is particularly no pattern coming out in this recurrence relation. So in fact, for this kind of recurrence relations, unfolding will not help. I leave you guys to check and verify and convince yourselves that here by unfolding you will not be able to guess the actual value. In fact, guessing the actual value is quite complicated here. Here is the actual guess. And you can see by looking at this expression, it isn't something that is easy to guess. Right? Also, we have other kind of formulas like this one, where b1 equals to 1 and bn equals to bn by 2 plus 1, where this one denotes the integer that is bigger than or equal to n by 2. So if n equals to 9, then n by 2 with these two things here is 5. Right? So with this kind of an expression, unfortunately, there is no clean guess can be made because of this extra bit of weird things that are there. This, what we call as ceilings. right? So there are expressions of this form where either the casing is too hard or we don't have a very clean casing for them. How to attack this particular kind of recurrence relations we will be doing in the next couple of weeks. Thank you.